so also welcome from my side. So in our first presentation, we want to take a look back into the beginnings of the FleXRay Lab, highlight some of the research projects of the last 5 years, and at the very end also dare to look a bit into the future. But before I begin, for those not familiar with X-ray computed tomography, well, let me actually see if I can get a pointer in here. Yeah, it's nice. So for those of you not familiar with X-ray tomography, here's a little animation. So think of them as really light that has very high energy, so high energy that it can penetrate even solid objects. So think about that we have this Playmobil figure here, and we put it in an X-ray beam, so that's the light, the white light that you see here. And then we put a detector behind it, and wherever the rays transverse the object, you see that it leaves a bit of a shadow, but you can definitely still see the internal structures. Now, if you do that from a lot of different angles, you can use a computational algorithm to compute an image of the interior of the object. And so in there, you can then see what's happening on the inside. And this is the setting of, from which you might be more familiar with. This is a medical CT scanner where we have the same sort of physical principle. Then computational algorithms, pretty much the same one, will give the medical doctor a nice image of the interior of the patient. And now our field, computational imaging, is the precise science of how do we compute these nice images. And it sits a bit on the boundary between mathematics and computer science. So mathematics provides us with the theoretical frameworks and the tools we need to develop algorithms. And computer science helps us and allows us to turn those algorithms into efficient computational code that can then compute these images as fast as possible. So down here you see imaging science. It's a bit the bigger field of sort of also involving physics and all the technology and the engineering of concrete machines, like say medical CT. And if you think about CWI as an institute, we got the mathematics and computer science really well covered. So in some sense, CWI is a perfect place for a computational imaging group like us that has a stronger methodological focus. But a bit the problem is that if, let's say, normally a group like us, doesn't have access to own scanning facilities. So if we have some new interesting idea and we just want to sort of test it out or play around, then it tends to normally get a bit difficult because we need to find a partner that has a scanning device. Normally these scanners are commercial machines, so they run a number of predefined programs, but they do not really let you play around. Like you cannot just go there and say, I want to use it now in this crazy new idea. So there's normally this sort of translational barrier here, which leads to the problem that it can often take very long for novel ideas to reach really the application. And so this is where our the group leader of our computational imaging group, Jos Bartenburg at the time, really had the idea to overcome this limitation and to break this barrier. So he wanted to create an X-ray lab that is accessible to mathematicians and computer scientists like us, where we, if we have a new interesting idea, we just walk into the next room where the lab is, and we have a scanner that is flexible and accessible enough so that we can actually test out these new ideas immediately. And so he set up a consortium. So besides CWI, this involved XRE, which is a company from Ghent in Belgium. It's actually a spin-off of a university center for computational tomography, about which we will hear later. And they are really making very innovative X-ray micro CT solutions, and so they were sort of a natural partner for, let's say, a scanner with which you can do more things than a usual micro CT machine. And they're actually outside in the foyer. They have a screen where they showcase their latest innovations, so you can look at that in the tea break. And besides that, we had NICEF and ASI, which stands for Amsterdam Scientific Instruments. So NICEF is the Dutch National Institute for Subatomic Physics, and both of them have a strong interest in developing novel detectors for X-rays that can differentiate the energy of incoming photons, and Martin will show you more of this work later. So within that consortium, CWI was sort of in the scientific lead. And here's a little video we found from actually getting the scanner into the institute. It wasn't so easy. You needed to put some plates on the floor, and then you needed to remove some windows and walls. And this is how the scanner comes in. And there it already gets unwrapped, so you might recognize some of the people in the video. And here's actually a look into the scanner. So you see the X-ray source moving around, and here's the rotation table on which we can place objects. And on the opposite side, we'll now see the detector also going up and down. And once the lab was sort of officially established, there was also an opening ceremony, pretty much 5 years ago. And we managed to find an old picture from back then. And besides representatives from the consortium, we also had the former State Secretary of Education, Sander Decker, here in the middle. And he launched the lab by hitting a big mysterious button. And yeah, so then this is sort of how the lab got started. Now, if you think about the lab, or what is the FleXRay Lab, you can of course start, let's say, and say, okay, it's a room within CWI, and we have this nice X-ray scanner in there. And if you look into the X-ray scanner, we got all the components on motor stages, so they can be moved independently. And we have pretty sort of low-level access to all the components. We can script the scanner to do pretty much anything we want. So it's really a flexible tool for trying out any idea that you have. On the other hand, the whole lab is linked to computing servers. So it's linked to a sort of a high-performance cluster, which is important for our work. But you can also think of the FleXRay Lab more in terms of a, let's say, on conceptual level. I think it's really a collaborative platform where mathematics, computer science, and the imaging science meet. So if we look back in this histogram, we used to be here, but now we're sitting really here in this nice sweet spot in the intersection. And it's also in practice that the collaborations that we have, about which we'll hear also later, are driving the research that we're doing. And this is best explained by some examples. And now here's the first disclaimer. So neither me nor Tristan were around when the lab was actually built and established. So a lot of great colleagues did a lot of great work there before us, and now it was sort of our task to pick the highlights, which is a bit of a dangerous task. And at the same time, we also didn't just want to make a long sort of list of this person that wrote this paper and this project, and now we move on. So the next slides will rather be a bit cleaner with just a few images, and you can find all the publications on our website or just ask us in the coffee break. And also whenever I say we did this or that, it's really the sort of metaphorical we. It doesn't, me and Tristan actually didn't do the work, right? Good. Yeah, so I start with, let's say, the most interesting, unique objects that we were allowed to scan. So they often came from collaborations with the cultural heritage sector or natural history, for example, the Rijksmuseum. So there were, say, very old bones, for example. There were terracotta statues that I'm going to talk a bit more about. There is this nice wooden statue that Marta will probably talk a lot about. We scanned an old book, and this became a bit the sort of poster model of what we can do. This is an ivory ball from ancient China, and this is the first object I'm going to talk about. So this is something the Rijksmuseum had, and they came into the lab, and they were actually interested first how these things actually look in the inside. So this is really concentric spheres, 13 of them, carved out of a solid piece of ivory. And it's really also, at that time, was not very well understood how they were actually made. So here's a bit then the workflow. We have the artifacts. It was scanned in our lab. We had to move the detector into 6 different positions because the object was so big. That created a lot of data, and then we would compute a reconstruction from that. And then the actually interesting part starts. So you try to understand the object now. So first you would, in this case, try to identify now how many spheres are actually in there and how are they connected. And once you have that, you can turn this object into a sort of digital representation with which you can play around then. So the researchers then were sort of able to see all the individual spheres or sort of turn all these individual spheres separately, and were able to realign them, and from that try to figure out how were they actually made. So they had some clues already, but during this research and by using these sort of digital representations, they could figure out which tools were used and in which order they were made. And you see the ones that are actually more on the inside look a bit less fancy and decorated, but these were the ones that you could actually not really see from the outside. Okay, here's another showcase. So that is a statue from the workshop of Michelangelo, and a big question was it actually from him or one of his students? Because very often that's not completely easy to identify. So here the question was, if we scan it, and we know that these statues are hollow on the inside, and they might contain fingerprints of the maker. So if we reconstruct it, will we find some fingerprints? And if we do, can we extract them and match them with Michelangelo's fingerprints, which are known from other objects where it's clear that and he did it. So that's another example for of a where sort of an object and an initial research question led to like a sophisticated workflow, and at the end sort of more and more interesting questions were coming up. And at some point we started to think of this in a bit more as a concept. We call it explorative imaging, where the idea is traditional sequential imaging flows often are done sort of in steps, where an expert comes to an operating facility, scans an object, is then given reconstruction and visualizations, and at sort of a later stage does a research and analysis. And the problem with these sequential workflows is that if something interesting comes up at this stage, you need to start over again and say, well, now I might actually detected a fingerprint now I need to go back and I want to do a more high resolution scan of a particular area. And the question was, how can we make this workflow more dynamic and incorporate the expert feedback directly into the scan process? So to sort of close this loop and have a more or less interactive direct feedback. And from the infrastructure that one would need for that, one would need sort of a very closed loop of fast data acquisition, a fast transmission to a server where the computations are actually done, and again a fast transmission onto a platform where then the reconstruction and visualization is provided to the expert, and the expert can in this process give feedback. And one particular development that came out of that is called Recast 3D. That's a software platform that we developed that can really do a real-time quasi 3D reconstruction. So at the time when you're scanning, you already have an idea of what's going on inside. And this now also was extended to a sort of plug-in infrastructure to not only visualize these images, but do immediate image analysis on them. So you could immediately do things like identify objects in them. And if you can do that, it gives you the capability to steer experiments in the X-ray scanner while they're happening. So for example, you can adapt the experimental conditions, or you can control what's going on. And for example, this is now in use in certain facilities, for example at the Tomcat beamline at a big synchrotron, the PSI. And this was actually the point where I wanted to take you into the lab, because we sort of planned this as a hybrid event. So there's people here, there's people on stream. So we know we couldn't take everyone into the lab and do a live demo. But originally we wanted to make a nice live stream into the lab right now. So we thought, okay, already setting up a hybrid meeting is not technically challenging enough. Let's put another layer of complexity on it. Let's do a live stream into the lab, right? And then let's have like 3 computers there that do a live scan and a live reconstruction. And we had it all sort of planned and rehearsed, and it all went well. And I actually prepared something nice here, a little cupcake with a 5 on it. And in there was a little chip that if we would have scanned it and we would have explored in this explorative imaging way, figured out that there's something interesting in there, would have showed something like this. And So in principle, until yesterday afternoon, this went all very well and was ready to go. But then our detector that reliably worked for the last months and years decided it's a very good time to stop doing that for a while. We will fix it probably within the next days, but for today, I'm very sorry. But if you're around for the 10-year anniversary, I will promise to deliver. So instead, I'm going to show you a video of how that in principle works. So what we have here is an ongoing live experiment, and here we just look at a tablet that's slowly dissolving in a gel. And on the right-hand side, you have a live reconstruction of that in the central slice. So while the experiment is running, you see it's turning around. You can see the reconstruction here, and you could decide now based on that I want to zoom into this interesting part here. So you can really adapt the scan parameters on the fly, and you see that also the reconstruction now understood that, okay, we're in a new setting and we zoom in. You can now see the fine features here. Okay. Yeah, so the last example already showed that we are often interested in dynamic processes. Here's another example. Here we look at a lava lamp that we put into the scanner. It's the first time we did fire in the scanner. Took a bit of convincing. And so this is an example of certain fluid flow systems that are interesting. And the problem if you do these dynamic scans is pretty much the same that you have if you have a mobile phone. You want to take an image of something that's moving, so you get a lot of blurring. And this is just an example of a reconstruction that you can do that tries to simultaneously not only reconstruct the motion that's going on, but also tries to understand what is happening in these different image frames. So it tries to understand where do things move, and this is depicted here in the bottom, these nice color plots. Each color here shows a bit in which direction are things in the image moving. Okay, now another big sort of part of projects is that, of course, these days, wherever you give a talk about something technical, you cannot come around talking about AI as well. And if you look in the area of image reconstruction, imaging science, then AI is really one of the most disruptive developments, and it's really a lot of potential. So this is an example that a colleague of us did. This is an X-ray scan of a fiber composite material. And this is a scan when you have a sort of high quality data. This is when instead you do a very quick scan, and as you can see, you can't really see any sort of fine structure anymore. And what he then did is trained a network on taking these slices as input and transforming them into something like this. And this is the result that the network then after training gave you. So you have to appreciate that I can pretty much not see anything in this very noisy image. So given that, it's a pretty fascinating result. So it really, when the lab was set up 5 years ago, AI really started to take off in image reconstruction. And it also sort of has shaped a bit the way that we do things, and it also led to a lot of new interesting research questions. So one of the biggest challenges here is really to translate AI from, let's say proof of concept ideas to things that really work in practical applications. When you do that, you will first notice, okay, compared to other areas like image processing, there's actually not that many good X-ray data collections that you can use for training these networks, compared to what people do, say, detecting whether there's a cat or a dog in an image. What we do typically works with 3D data that's really big. Robustness is a big issue. So if you think about medical imaging, then you need to make sure that the networks that you use sort of, it's explainable of how they get to their decisions and that they don't do anything weird. And there's a couple of other elements in here as well. So from that, I just want to show some quick results. So we started, when we started, we noticed that there's barely any good usable open data collections for machine learning out there. And this was really something where our lab could kind of come in handy. So we started to, so our first data set was just from walnuts. And you might ask, okay, why walnuts? I mean, one thing is you can radiate walnuts as much as you like. They don't complain. The other thing is if you look at their structure, so they have a bit of hard shell, a softer inside, variety of fine to scale structures. It's a really good proxy for the human head to some extent, because we looked into, that was a collaboration with people that looked into skull imaging, and so we took a couple of those, we scanned a lot of those walnuts, and we made a data set from which you could then train networks, for example. If you have a particular scanning setup that you also have in skull imaging, the images that you get often suffer from artifacts. But if we combine the data we have cleverly, we get nice sort of ground truth reconstructions. Then you can train network to try and remove those artifacts. Here's just an example of how this works. So this is like the input image, where you see that on the top part of the head you have very big artifacts. This is what the network is supposed to train. And after some training, this is sort of the solution we came up with, where you can see it can really do a good job taking this input and getting very close to the target. Yeah, so all of our, or most of our data sets are now openly available. So there's this great data sharing platform called Zenodo, where we have an OMCON Unity. So we have a lot of data sets there for all sorts of purposes. So if you're ever in need of any data, have a look at that, or otherwise let us know. And another thing that sort of an application where we use that is to sort of on the fly increase the resolution of images that we scan. So imagine that you have a big object, like in material science, that consists of many parts that are sort of self-similar, and you don't want to scan the whole big object because that would take too long. But instead, you just scan the big object on a very coarse, rough resolution, and then you just scan one particular part in a high resolution. And then you try and train a network that should learn, now given the information from this high resolution region and the big coarse resolution, how can I improve the resolution in the whole image? And this is just an example. This is the low resolution input. That's the high resolution ground truth data that the network trained on. And from this input, the network can then output something like this, so really improve the resolution over this coarse initial case. Good. That's another project that was concerned with the problem that very often we want to do very fast scans, and the volumes that we get are very big. So traditional machine learning techniques are typically designed for 2D moderate scale scenarios. But here we really go into large-scale 3D stuff, and here the idea is that you can combine traditional image reconstruction techniques with shallow machine learning applications, and then get things that have the same sort of runtime as the fast solution, but improve massively by using machine learning on top. Now we get to another data set where we scan some fruits. This time it's apples. So this is the work of, or that came out of a code sprint, so a sort of collaborative workshop where researchers from different countries came here to CWI to work on a topic for 2 weeks. And the idea there was that while there is a lot of, machine learning approaches out there, but it's very difficult to benchmark them, or it's very difficult to compare them. So the idea was, let's gather a big data set, and each group sort of implements a different machine learning method, and then we test it all on the same data set. And this is just a result. This is a slice through an apple, where you can see that some of these spots here are brown spots. And the question was, when you lower the number of projection angles, what are the different approaches still able to to recognize? The results don't matter so much. The idea was more that we sort of use the lab to provide a bit of a benchmarking standard here for this question. Okay, and yeah, you might have already seen that, or you might have already asked yourself what's so interesting about apples or walnuts, all these things. And you wouldn't believe how many sort of different types of food we already scanned in the scanner. So it's sort of our PhD students are notorious for going to supermarkets and just buying anything that you can put in a scanner. So one of the reasons is that we have a couple of collaborations with the industry where the idea is that one would like to use X-ray imaging in quality control. So you can really think a bit about it like that we are back to apples that go on a conveyor belt, and there might come through stages where you do some sort of X-ray scanning, which gives for this particular apple sort of digital passport that's attached to it. Then there's some sort of real-time analysis going on that might, for example, identify, oh, there's a problem here in this apple, and based on that there will be some automatic decision making that either says apple's good, apple's bad, something needs to be done here. And what we do for these things is often that we use the FleXRay Lab to remodel typical scanning scenarios that might occur there. So this is one example where one might think that in an industrial process line one would make a sort of turn here in the conveyor belt, have a source and detector here, and sorry, let's play this again. So the apples would sort of go through this in a bit of a carousel, and with the scanner that we have, we can simulate these things before they are designed, or we can test certain configurations, see what type of images can we get, what type of challenges lie in the image reconstructions. And sort of as my last example of this sort of emulation, a bit more sophisticated example, there is the idea that in X-ray imaging one could also do what you can do in normal sort of light field cameras, something where you take different images or with a different sort of lens system that later after the acquisition you can zoom in or sharpen certain areas in certain depths. And the idea is for X-ray imaging, the optical instruments that you would need for that are still being developed, or it's much more difficult to develop them. But this was work in a big European project, so where specific experimentalists were developing these optics, and our idea was, okay, with the scan or with the lab that we have, we can already mimic the type of data that these devices would collect. And based on that, we could already design the image reconstruction pipeline and could already decide on certain design parameters and figure out what will these methods actually bring to the table. And this is one example here where we imaged a certain structure here that's actually just a branch from a tree, but you can think of this as something that looks a bit like blood vessels. And with this very sort of light field imaging, which is really a very projectional imaging from one side, we could sort of reconstruct images that very accurately map out the depths of these structures, even though we did not do a fully 3D scan of the object. Great, and with that we come to a different part of the presentation, namely Martin from NICAF will now tell you a bit about the spectral imaging that's what's going on.
Okay, thank you. I'm Martin from NICAF. One of the collaborators in the FleXRay collaboration, and the idea is to talk a little bit about the detector. It's a detail inside the whole thing, but I will show a few things why you can say, okay, why spend some more attention on the type of detector that you would like to use. Works? Yeah, okay. So if you look at a conventional X-ray image, on the left you have an X-ray tube. These things put out a broad band of different energies of X-rays. So it's sort of a wide light source consisting of all kinds of colors. You have the subject, the sample, and a detector. These detectors, in general, they only detect the amount of energy that's alive, and they don't care about the number of photons and energy. Sorry. Oh yeah, thanks. Is this better? Yeah. Okay. So these detectors don't care much about the individual photons. So the result is an image in grayscale values. So some information gets lost. And the idea is, if you look at a graph of X-ray transmission through, in this case, 3 thicknesses of different metals, you can clearly distinguish a lot of features in there that give information about these materials. The first thing that you can see is materials tend to get more transparent for higher X-ray energies. So for, let's say, more bluish light in X-ray words. The next thing that you can see is that elements have very distinct lines in which the transparency changes. This is related to binding energy of electrons in these materials. So these are unique for all the elements. So that's information in there. So you can imagine it should be easy to identify these materials. So the problem is when you integrate energy, that's why I choose these weird values for these thickness of metal foils, they all would have the same level of gray value. So they would be indistinguishable in a fairly standard scanner. Another implication of this is that high energies easier make it through the whole sample. So the spectrum of X-rays is changing as it is going through the sample. And as a result, this effect is called beam hardening. As a result, the sensitivity to thickness changes of the sample depends on the thickness itself. By the way, is this actually okay, or should I stay here? It sounds a bit... Yeah? Okay. So the sensitivity of your system depends on the thing itself. You don't want it. So what you could do is, would be nice if your detector could actually count the individual photons. That already helps in sort of giving more weight to the low energy photons. In general, improving contrast, because low energy photons are better absorbed, so they have more contrast in the image. And even better if you could measure the energy of the individual photons and add this color information. But before I say, hey, this detector is the best thing and the only solution, in general, what a common alternative is, with a few drawbacks, is that you tune the X-ray spectrum itself. So you're not necessarily stuck with one X-ray source, so you can apply filters to select certain energy bands and to also do some sort of spectral X-ray scanning with fairly conventional equipment. So if you now replace this detector with a pixel chip that detects charge, very similar to the pixel chip in your phone, like the image sensor, which detects charge released by visible light. On top of that, you apply an X-ray sensor, and inside this X-ray sensor, you get an amount of charge proportional to the energy of an X-ray that's being absorbed in there. Then you will be detecting individual photons, so that's already one thing. And the Medipix 3 chip, the Medipix 3 based detector that's in FleXRay setup, is able to set 8 different threshold levels. So you can sort of make 8 energy bins, so you see 8 different levels in the energy spectrum that you're scanning. Just for the idea, these are the physical detectors. I brought one of those. So, can you understand me in the back, by the way? Yeah, okay. So for online. Oh yeah, I'm sorry, for the online people. Yes, okay. So this is one of the Medipix detectors. As you can see, the field itself is quite small. It's 3 times 3 centimeters. But the idea is that you can at least take parts of the sample or a small area where you can look at these new different properties of the sample itself. So on a small scale you could do some spectral scanning. So if we now go from a black and white image, which in this case is a pack of metal foils on top of a sensor, now you see just a bunch of gray values, no idea of what the material is and how thick it is. If you add this energy information, you can immediately see, based on assigning colors to the energies that you detect, what kind of materials are in there, based on the color. And that also helps you to tell something about the thickness of this material as well. So now you certainly can differentiate cadmium, brass and steel, for example, which are more or less, especially in this lighting conditions, are the same level of black in this sheet over here. So and you can also make a scan through an energy spectrum, and that's showing a little more clear of what's happening. Here are those metal foils again, and as you can certainly see the changes in transparency of these metals. Those are these very characteristic lines that you could see in the graph. So these really help in identifying these materials. But also for materials that don't have these lines in the energy spectrum that we are looking at, you can still use spectral scanning to look at certain features in the sample. Example, this is one of these eggs that you can buy in the supermarket. They're called kwartel-eitjes. And sometimes there's the unpleasant surprise of an embryo in there, something else, you don't want to have this on your plate. But it makes a nice object for in the scanner. And as you can see, for the low energies, you can see more detail in the soft tissues. And the higher energies allow you to zoom in more on the dense tissues. So also there you can get more information from your sample. So if you now go to the CT scans, well, this is an example of a CT scan. This was actually made in the FleXRay cabinet of a small snail shell with a few beads in there. And as you scan through it, you may be wondering what would be the added value of spectral measurements here. Well, I just saw that you can do great things with artificial intelligence, because I was really surprised by seeing, hey, they removed the artifact, I do call this the beam hardening artifact, by recognizing it using artificial intelligence. But spectral imaging also helps a bit here. As you see, here is a slice of the reconstructed object. On the left slice, it's the full energy spectrum up to 35 kiloelectron volt. And there you can see a few beam hardening artifacts. One of them is this density gradient that seems to be there over the sample. And the other thing is, okay, maybe you don't see it here, but there's a little smudge on the side of this blob, which is not there. And if you select a certain energy band, then you can see that there's a fairly uniform, yes, thank you. You can see there's a fairly uniform thickness or density in these materials, regardless whether or not you want to identify these materials. So that helps you out with beam hardening artifacts, which is bringing me to the end of this short presentation on Medipix. So the idea is that this detector allows you to do photon counting and make energy bins in the spectrum that you want to scan. These detectors, they can be mounted on top of the scanner that's in the FleXRay cabinet, but since that was a bit tricky, we now also have at NICAF a setup, a micro CT setup, where we can just put something in and scan something small, like in this case the bumblebee that you see in there. So that is the Medipix 3 detector in the FleXRay Lab. So that's it.
Thank you. I'll switch to the other microphone. And to the next slide. Yes, all right. Good, so now it falls to me as the new group leader of the Computational Imaging group to then also talk a little bit about the future. So we've seen what we have achieved, we've seen the really exciting things that can be done if you give mathematicians and computer scientists an X-ray scanner. So now let's try to look a little bit into the future. There we go. So as already highlighted by Felix, for us, right, this FleXRay laboratory, it's really a collaborative platform where we can bring together mathematics, computer science, and imaging science in various applications, involving the domain expert in scanning. And this really goes beyond, right, the traditional paradigm of open science, right? This traditional paradigm is I publish my algorithm, somebody else publishes their data, and somebody can put it together, right? Maybe we do or maybe they do. Here what we do is we bring everybody together, making sure that together, right, we can apply these algorithms, tweak them if necessary, acquire more data if necessary, and in that way can really contribute to generating new science. This has already proven to be very successful in larger collaborations, right? So in projects that we have in collaboration with the Rijksmuseum, for example, or the food industry. But we believe it can also be very successful for short-term collaboration. So just bringing in scientists for a couple of days, scanning some things, analyzing the data. And later today we'll actually see some of those projects already highlighting this added value. What is needed to continue to contribute from the mathematics and computer science is new developments. And what I'll now do is try to highlight what I think will be 3 important topics for the foreseeable future. The first one I'd like to highlight is adaptive scanning. So Felix already mentioned this idea, right, of adapting the scanning protocol while you are scanning by having a real-life visualization. But what we'd like to do is really take this a step further and have automatic adaptive scanning. So having the scanner automatically adapt to whatever you put in the cabinet, and then figure out what needs to be done in order to answer the question that you have. And it sounds very simple, but if you really think about it, it's actually surprisingly hard to do well, right? First, you need to somehow know what is optimal, what should it adapt to, what would I like to see, and then it should figure out how to adapt to it. So what is needed for this is first, right, mathematically modeling the questions that you may have about the object, and then figuring out how to adapt the scanner to it. So this really brings together various topics, including Bayesian modeling, optimal control, reinforcement learning. So again, kind of highlighting how mathematics and computer science can benefit these type of applications. The other development that I can see for the coming years that I would like to highlight is quantitative imaging. So Martin already really nicely highlighted the added value of having spectral information available, but he also kind of highlighted the challenges that there are then in acquiring the data and also in the image reconstruction. So what is needed to really extract information from every photon that you measure would be a much more detailed mathematical model of the underlying physics. Consequently, the image reconstruction step will be much harder to solve. Simulating the underlying physics itself, there are many ways to do that, but then to incorporate that in a useful way in image reconstruction also then requires again bringing together various areas of mathematics, including recent developments in physics-based machine learning to really make this happen. So what you see here in the picture is kind of an example that highlights again what Martin said. So in gray you can see what would be the conventional image that highlights contrasts if you're lucky, but doesn't completely tell you which material. And then ultimately, if we're successful, what you can do is then identify materials, but on top of that also get information about trade-offs or uncertainties. So what you'd like to know, for example, is this material here, am I 100% sure it's this particular density, or is there some potential variation in that? And going forward, I think that this is needed for rigorous analysis of these type of images and use of them in a like a whole pipeline. So the last thing I'd like to, I'm not actually using these. The last thing I would like to highlight now is that so far we've been looking at images, but what I'd like to convey and think about in the future is that we need to go beyond images. An image is basically just a snapshot of a particular view on the data, It's a window into your data, and you'd like to explore also there your data in multiple ways. What is the challenge there in computational imaging is that your data, what you record in the scanner, and your final image are connected through a computational pipeline that usually takes minutes or maybe hours to process. In this pipeline, you've made many choices about processing the data, about which reconstruction algorithm to use, about which prior assumptions you have, and all these choices will have an influence on the final image. So what you'd like to ultimately be able to do is to track back the influence of the various choices that you made on a particular feature that you are interested in. And then maybe figure out that if you're interpreting the value of a particular pixel, is that dedicated or is that dictated by the data, or is that somehow informed by one of the choices that you made along the way? And again, to do this, what is needed are, bringing together developments in mathematics and computer science to make this happen. So I'd like to then repeat again, right, the schematic that Felix showed earlier with a small tweak, right? We're not just bringing together mathematics and computer science and imaging science, but we're bringing together all the people involved in this. And to have all of those in one place, as we have here today, that's really what I think the added value of such a lab and a place like CWI is. So with that, we'd like to acknowledge some people. We'll do that together with Felix, and then we'll have a coffee break.
So first of all, we would really like to thank Joost. So Joost for sort of, setting all of this up and really realizing your vision of the FleXRay Lab. Then next is that we of course want to thank everyone in the consortium that was behind setting it up. In particular XRE for all the continuous support on sort of technical levels and so on. And writing the slides, I didn't know how sort of recent that would be. So thanks a lot for that. Because by the end of the day, we're sort of computer scientists and mathematicians. So we also need some good engineers. Most importantly, Sofia Vesnikoban and Alexander Kostenko, two postdocs here that were really there for the lab from the start and really sort of built it all up and sort of shaped also all the workflows that we're still using today. So without them, none of what we showed you would have been possible, or we could have done that. And then, in particular, also Willem Jan for also all sort of the technical or help with technical problems as well as solutions over the past 5 years. Navreet Baal, mentioned by Martin, has done a great work on the MedicPic scanner and in the FleXRay Lab. And finally, we want to thank really all the computational imaging group because they really made sort of the lab into a lively, exciting place where we can do fun research. That's very important.
And thank you, Felix, for putting together the nice program for today.
Yeah, and of course all the partners and sponsors. Again, it's a dangerous slide because we probably forgot someone, so please don't be angry at us. And thank you all for coming, and I think that's a great time to